Okay. Hi, everybody. A very good evening. So I see only 3 of you. Is there any exams going on today? 4. That's joined. Is it okay. Fine. Now I think slowly people are joining. Okay. Fine. Let me share my screen. So we were seeing coordination compounds, right? We started with coordination compounds. Right. So I think we started with what do you mean by coordination number and what is oxidation number. And these are the different names, symbols of different ligands. We saw what are the different classification of ligands, right? And we said we also talked about what is the characteristic for a central metal atom, how it should be for it to have a coordination complex, is it not? It should have a small size, high amount of charge, large number of large number of oxidation numbers, right? All these things will be possible. Then we saw about different types of ligands, right? We saw, okay, one of them was chelating ligands. So we remember where density is greater than 1, then you will always form a ring structure. Okay, now that ring structure, that ring formation, that process is what is called as chelation, right? And the ligand which is involving in chelation is what is called as chelating ligand, right? Or chelating ligand, however you want to call it. Then we have ambidentate ligands, that is, we are going to have 2 centers for donation, but at a time, only one of them will donate, right? Like NO plus, SCN minus, right? All these are different examples, right? Say I can have NO2 minus, or I can write ONO minus. Nitrogen going to have negative charge, oxygen going to have negative charge. Here I can write NCS minus, SCN minus, or NCS minus, something like this, right? All these are going to be ambidentate ligands. Then we have something called as flexidentate ligands, in the sense that they are going to be bidentate or tridentate, but they can modify the densities, right? It's not necessary that all the donor side should be active in a compound, right? And then we saw the monodentate, didentate, all the examples, right? And then ligands with respect, we saw what are ligands? Ligands are the one which are going to be acting as electron donors, right? So we understand that in a coordination complex, right? In a coordination compound, inside the bracket, whatever is coming, right? All the bonds you're going to see are going to be coordinate bonds, right? So metals will accept electron and ligands will donate electrons, right? So now we can have a positive ligand, negative ligand, neutral ligand based on the charge. Then I think we saw what are coordination compounds, right? Double salt. What is the difference between double salts and coordination compounds? It's all about how they're going to ionize in water, right? So in case of a double salt, whatever the ions you expect will definitely come, right? But in case of coordination complexes, no, you're going to get something different. You're going to get a bracket, square bracket, and that is going to be one entity. And we are going to have something called as a counter ion, right? All those things we saw, right? So now we'll continue, right? We'll continue with this, right? So now today we will be seeing how to write the Iupac name of an coordination compound. Okay, how to write the Iupac name of the coordination compound, right? So there are certain rules which you have to follow, right? So the first rule is that you must always name the cation first, right? Then only anion next, right? So see again, the counter ion can be positive or the coordination sphere can be positive, or say again, it can vary, right? Again, the anion can be coordination complex or the counter ion can be coordination complex, doesn't matter, right? So what I understand is first you have to name the cation, then only we have to go name the anion, right? So for example, if the counter ion is the one who's going to have a cation, you have to start with the counter ion first, then only go to the coordination complex. Okay, right? That is the first rule which you have to follow. Now, second rule is that whenever you're going to name the coordination sphere, right? Whenever you're going to name the coordination sphere, right? Whether it's cation or anion, whether it is going to come first or second, doesn't matter, right? Whenever you're going to name the what is that coordination sphere, you have to name the ligands first, right? You have to name the ligands first, then only you have to go for the metal, right? Metal second. Okay, you have to name the ligands first, then only you have to name the metal. Okay, now whenever we are going to name the ligands, right? Say if at all, whenever we are going to name the ligand, right? So please understand that the number of ligand is very important, right? Number of ligand has to be mentioned, right? Now please understand, for number of ligands you'll be writing two things, right? One is say di, tri, tetra, something like this. Now you will do this for monodentate ligands, right? If at all you have monodentate ligands, the number of ligands will be specified by di, tri, tetra, penta, something like that, right? Now, if at all you will be using this bis, tris, tetris, like this, right? When you have polydentate ligands, generally more like anything other than monodentate. Okay, right? So if at all you don't have monodentate ligand, but you have a didentate or tridentate or any other polydentate ligand, right? You will be using this bis, tris, tetris. That is how you will be writing the. You will be mentioning the number of ligands. Okay, right? You'll see more examples. Don't worry, right? I'm just giving you the rules. Next, right? Again, whenever you have more than one type of ligand, more than one type of ligand is there, right? More than one type of ligand is there, we have to follow alphabetical order, right? We have to follow alphabetical order. Okay, right? So whenever you have more than one type of ligand, like say chlorine is there, bromine is there, then you have to write bromine first, then you have to go for chlorine, because B comes first in alphabetical order, then only comes C, right? Okay, now the last point is when you talk about the metal, central metal atom, right? When you talk about the central metal, right, you have to include the oxidation number, right? The oxidation number in Roman letters. For example, if the oxidation number is +1, then you'll write 1 like this. If the oxidation number is +2, then you'll write 2 like this. Like this, you have to mention the oxidation number, right? So for example, if iron is in +2 oxidation state, right? Now, how do you write this? Iron 2. You'll write like this in the ring. Okay. If you find that the iron is going to be in +2 oxidation state, how do you write? You write the full name of the metal, iron, right? And then you will write the oxidation number in the brackets. That too in the Roman numbers, Roman letters. Okay. So these are all the points which we have to follow in writing your Iupac name of the coordination complex. First and foremost thing, we have to name the cation first, then the anion. It doesn't matter whether it is going to be a coordination complex or the counter ion. Whatever it is, first the cation, then the anion. Okay, right? Okay, one more thing also I forgot. Right? If you find the coordination complex, right? If you find the coordination complex to be a negative charge, right? If you find the coordination complex to be a negative charge, you have to end with 8. Right? Whenever if you find the coordination complex is going to be the negative charge, the counter ion is positive, right? If the counter ion is positive, and if you find that the coordination complex is going to be negative, right, you have to end with ATE, right? For example, like you have to end with, say, for example, ferrate 2, something like this, right? That is how it ends, right? Because you have a counter ion, say some A plus, and inside the complex you have this that is going to be a negative charge, say for example, right? And say I have the ligands and all, you will first name this first, right? You will name the cation first, then you will go into the coordination sphere, name all the ligands, right? Then you will go for writing this ion, right? Then you'll write for going this ion, the metal. Okay. Now that ion, say, is in +2 oxidation state. Now you see that this is a negative charge. So you will end, like you will write all the names and end with ferrate 2. This is how you must end. Okay. Right. So you have to, and normally, if at all you have the coordination number to be a positive charge, sorry, coordination complex to be a positive charge, normally you write, you just end with iron, nickel, copper, something like that. That's it. That's how you have to end with. Okay. Right. So that one you have to remember. So these are, and then what we said. Okay. So whenever we go for the coordination complex, you have to name the ligands first, then only the metal, central metal atom has to be named. Right. And whenever you speak about the ligand, the number of ligands has to be specified. Now, if you have monodentate ligand only, then you'll use the di, tri, tetra for specifying the number, right? If at all you have more than monodentate, didentate, polydentate and all, you have to use bis, tis, tetris, everything, right? And if you have more than one type of ligand, the naming of ligand should be done in the alphabetical order, right? And whenever you talk about the central atom, we have to include the oxidation number in Roman letters. Okay, right? And at last we saw this coordination complex. If it is negative, you have to end the name of this thing with ATE, right? So we will take some good examples now. Okay, right. So let me do one thing for you, then we can do the other things, right? So we have, say, K3, Fe, C2O4 thrice. Okay, this is the complex we have. Okay, right. So now for us to understand this, see, it is very easy to understand whether the coordination complex is going to be positive charge or negative charge, because whenever we write the formula, right? Okay, whenever we write the formula, we write the cation first, then only we write the anion. Is it not? Do we write, say, sodium chloride also? Like if I say NaCl, why we write Na first? Because that is the positive charge. Why we write Cl minus next? Because that is the negative charge. You don't write ClNa. That doesn't make sense at all. Is it not? Because we always write the cation first, then only we go for the anion. In your coordination complex also, we follow the same thing. Now you can understand, right? Obviously, K is going to have the positive charge and this one is going to have a negative charge. That's why you write like this. Okay. So there is no technique in finding out whether the coordination complex is going to be a positive or negative charge. It's very simple to understand, right? If the counter ion comes first, then that is positive. Then the coordination complex is negative. If the coordination complex comes first, that is going to be positive and the counter will be negative. That is very easy to understand. Right. Okay. Now, what is the first step? The first step is that we have to name the cation first. In this case, the cation is potassium. Right. Potassium. right? Now we are going to name your coordination complex. Now you can easily understand that it is actually going to be 3K plus, right? And you are going to have FeC2O4 thrice 3 minus, because the cation and anion, the amount of positive charge and negative charge should be same. Only then overall it will be neutral. Is it not? Okay. So we have potassium. We have named the cation. Okay. Now you don't have to specify how many potassiums are there. That is not important. Okay. Okay. Now you don't have to write tripotassium or something. It doesn't matter. Okay. Whenever you write the counter ion, you do not have to mention the number of counter ions. Okay. Right. So now we have mentioned the cation, potassium. Right. Now we are going to name the coordination complex. Now, whenever we go for the coordination complex, which has to be named first? I told you first the ligand has to be named, then the central metal atom should come. Now you understand that the ligand here is what? C2O4 2 minus. What is the ligand, people? What is this ligand?
Oxalate.
Yes, right. It is oxalate, right? And we have to understand, I told you the name, whenever you write the name of the ligand, we always replace this E with O, right? We write oxalato. Right, that is how we write. They give the normal name of the ligand is oxalate only. No issues, right? But whenever you write in the Iupac name of the coordination complex, right, that E alone should be replaced with what? O. Okay, oxalato we write. Okay, now we definitely know that there is a bidentate ligand. We have the charge like this, right? COO minus, COO minus. This is what is oxalate ion, right? And we have 3 such oxalate ions, is it not? So we'll write tris. Why tris? Because whenever we have only monodentate, then we go for di, tri, or tetra, right? If at all we have some other thing like this, that is didentate or polydentate, we have to mention the number of ligands with the help of what? With the help of bis or tris or tetris, something like that only. Okay, so we have 3. So I write tris, right? Then you write the name oxalato. Okay, done. You're done with the ligand, right? Tris oxalato. Okay. Now comes what? Now you're done with the ligand. Then you can mention the central metal. The central metal is going to be iron. Okay. Now you have to find the oxidation number, and for that we need to calculate it, right? So let me keep it as X. So you forget about the what is that? The counter ion, right? So we have X, right? So we have COO 2 minus. That is sorry, C2O4 2 minus is what is the charge. So can I write X minus 6? Why? Okay, this X6 how it came? 3 into minus 2. That's how it came, right? Is equal to minus 3. So can I write X is going to be plus 3. So that means iron is actually going to be in plus 3 oxidation state. Okay. So now how do we write? No, we should not write ion. Okay. If at all, okay. Now this is going to be a negative ion, right? The counter ion here is going to be negative. And I told you, whenever you find that the counter ion is going to be negative charge, we have to end with what? We have to end with ATE. Right? So we cannot write ionate, right? That is not the name. You have to write ferrate, right? You should not write iron, but you should write ferrate. Ferrate, and I told you that you have to mention the oxidation number in the Roman letters in the brackets, right? We understood that it is going to be in plus 3 oxidation state. So 3. This is the name of this particular complex. Okay, potassium, tris, oxalato, ferrate 3. Okay, right. Let me give you another one. Let me solve another one. Okay, so the second one is PT, NH3, thrice, NO, Cl2, Br2. This is the complex we have, right? Now again, you understand the first thing is to find whether which is positive, which is negative. This is positive, this is negative. No doubt, because whatever we write first, that's your positive charge, right? So for in this case, you have to name your coordination complex first, then the counter ion. Okay, right. Now what do we do? Now again, irrespective of whether it is going to be positive or negative, we have to name the ligands first. right? Now, what are the ligands here? Here, the ligand, the name is amine. We have to know the names. We have to be very careful. This table is very, very important. Okay, this table, where is amine? Hey, NH3, where are you? Yeah, look at this, right? This one, right? You see, the name is amine, right? Okay, now NO, nitric oxide, right? Is we have, but again, we have to choose whether it is going to be NO or NO plus or NO minus. Okay, most of the cases it is going to be NO plus. Do we have NO plus? Positively charged. Yeah, right. So remember, this is the most of the cases it will be NO plus. Okay, whenever NO comes, blindly go for this. It is going to be NO plus ion. Okay, 99.99% of the cases. Okay, right. So the name should be nitrosonium. Okay, the name should be nitrosonium, but let me check one more time. Just a minute, if it's correct or not. Nitrosyl. Okay. Fine, people. In this case, they're taking nitrosyl. That is NO, that is neutral ligand. Okay. Fine, we'll follow this only then. Right. So remember that whenever you find NO, it is always going to be a neutral ligand, and we'll be using the name as nitrosyl. Okay, forget about NO plus. Right. Mostly, I expect that they shouldn't be asking you NO because it will be very confusing. But if they ask you, blindly go for this. Right. You go for NO, a nitric oxide. That is neutral ligand is the ligand here. Nitrosyl is the name which you'll be using. Okay, fine. So NH3 is amine. This is nitrosyl. Right? And I know Cl2, how should you write? You should write it as chlorido, not chloride. I know the E should be replaced with O, right? So again, we have to follow alphabetical order whenever we go for more than one type of ligand is there now, right? There is more than one type of ligand. So obviously we have to follow alphabetical order. So obviously this should come first, this should come next, and this should come third. That is the alphabetical order. Okay. And you have to mention the number of ligands also. Now in this case, all are monodentate ligands. Right? So in this case, you have to use only di or tri or tetra, something like that. Okay. So we have this one first, right? So we write triamine, right? Then comes chlorine, and we have two chlorines. So dichlorido. Okay. Then comes nitrosyl. Only one nitrosyl is there, so no problem. Nitrosyl. Then it is platinum. Right? Then Pt is what? The center metal atom is platinum, right? And we have to calculate the charge. We have to calculate the oxidation number. For what you have to do, you can easily understand that it is Br2 means what? We have 2 Br minus, right? So obviously this should be 2 plus, right? This should be 2 plus, is it not? Right? So now let us calculate the oxidation number. For platinum, it is X. For ammonia, it is 0. For NO is also it is 0 because it is neutral ligand, right? And for Cl alone, it is -2. So we have to write -2 is equal to +2, right? So if this goes here, you will find that the X is going to be in what? +4 oxidation state. Okay, +4 oxidation state. So you will have to write that in the Roman numbers. Platinum 4. Now you see I'm not writing platinate. Why? Because here it is going to act as a positive charge, right? So we just write platinum, that's it, normally. Okay, platinum 4, then comes the counter ion, which is bromine. We will write it as bromide. That's it. This is how we write the name. Okay, right. Now, sometimes, right, you will be, I hope everybody is following. Anybody has any questions? How am I doing this? Okay, fine. I hope everybody is following. Yeah. So sometimes you can have both the coordination complex and the counter ion both to be coordination complexes, in the sense that both the positive charge and the negative charge both can be coordination complexes. Okay, that type of complex also is. For example, like this, right? Say third one. Let me solve it for you. Right? Say I can have something like this: Cr NH3 6 times. Okay, Cr NH3 6 times, and then you have CO. No, I should write CO like this. CO, that is cobalt, right? And you have Cn 6 times. Now what do you see? Both the positive charge and the negative charge is actually going to be the coordination complexes. Is it not? Right? Okay, fine. So we have to do something about this. Right? Okay. Now how do we do this? Right? Now it is very simple to understand, people. Now, see here, you have this to be a neutral ligand, right? This to be a neutral ligand. So whatever is the N plus you have, that much N minus also you should have, right? Whatever the N plus you have, that much N minus also you should have, right? Now I know Cn minus, Cn is going to be minus, that it is going to have a -1 charge, is it not? So obviously I can write like this: X minus 6 should be equal to minus, right? Whatever is the number, right? Okay, fine. For these kind of cases, we have to know what are the common oxidation states. Okay, so remember, people, for cobalt, it is actually going to be +3. Okay, +3 will be the oxidation state. So here you will be getting this charge to be -3 here. Okay, so you can write X to be +3. Okay, so now once you do this, okay, here you can go, right? Here you can have X -0 because this is done, right? So obviously, if this is 3 minus, this should be 3 plus. Okay, if this is 3 minus, this should be 3 plus, right? So I can write X is going to be again going to be in +3 oxidation state. Okay, right? So these and all this alone will come from practice. How do you write the what is the oxidation numbers alone for these kind of things will be little difficult because this you have to know sometimes, right? But other than that, the naming is very, very simple. Okay, right? So how do we do this? Again, you have to write the cation first, right? So again, whenever we write for coordination complex, we write the ligands first. Here I have amine to be the ligand. We write hexa, right? Because we have 6 hexa, amine. Now we have chromium. Now this is a positive charge, so we don't have to end with 8, but you have to mention this thing. What is that? Oxidation number: hexaamine chromium, right? Then go for the anion. Again, the ligand has to be named first, right? We can write hexa cyanido, or you can, instead of cyanido, you can just write cyano also. That is also correct. Okay, both cyanido as well as cyano, both are correct. Okay, right. So then cyano or cyanido, right? Hexacyanido. Then you go for the name of the central metal atom, that is cobalt, right? Can I end with cobalt? No, right? Because it is going to be a negative charge. We have to end with 18, cobaltate, and write the oxidation number +3. This entire thing is the name of this particular compound. Okay, right? So I will give you now more examples and you will be solving it now quickly, right? Okay, so we have this fourth one: CO, Cl2, En twice, Cl. Go for it. Tell me the name. So how do you write En, people? What is the name of En? En is a short form. What is the name of the ligand? En. What is the name of the ligand? I'm not able to hear what you're saying.
Ethane 1,2 diamine.
Ah, right. Ethane 1,2 diamine. That's the name. Right? Yes, the name is done. Anybody wants to tell me what is the name? Nobody wants to tell me the name. What is the name, people? Maybe I'll ask one specific person. That'll be fine. Okay. Akshaya, are you there, Kana? Akshaya. Yeah. Okay. Can you tell me the name of this compound? This compound. Okay. I don't know what is the so much tough thing to do here. It's very easy only, right? Okay. Now first,
Dichloroethane.
wait. First, this is your positive charge, this is your negative charge. Okay, so you're doing it correctly that you are naming the coordination complex first. In the coordination complex, which has to be named first?
Cation.
We have decided that cation is this, anion is this. Okay, that is okay. Now, obviously, we are going to name the cation first. Now, cation is the coordination complex. In the coordination complex, which has to be named first?
The ligand.
Ligand has to be named first, but how did you start? You start something with cobalt, something that is absolutely wrong, right? You have to start with ligands, right? So here the ligands name are chlorido, and here I have what? Bis. Oh, no, I only told the name. So sorry. Right. So here it is going to be ethane
1,2
diamine.
So should it be dichloro and
Yeah. I'm just telling you the name of the ligand. Yes. Right. Name of the ligand is chlorido. Now you have to mention the number. Obviously, that you have to do. Right. Yeah. Someone wants to try now the name completely.
Dichloro.
Dichloro. That's how we write.
Dichlorido. This ethane 1,2.
Then correct. Tell now correct. Then
cobalt.
Cobalt.
Then cobalt. Okay.
Then the oxidation state.
Oxidation state is what? Guys, how many of you are sitting with a pen and a notebook? If you are not sitting with a pen and a notebook, this does not make sense. What is the 2? Okay, let us check. Right? So here it is plus, here it is minus because only one chlorine is there. So we can write x minus 2. This is 0, right? This has no charge. So x minus 2 is equal to plus 1. So x should be what?
3,
plus 3. Right? X should be plus 3. Right? Okay. Yeah. So the name goes like this. How do you write? We have dichlorido, right? Because you have 2 chlorine. That is a monodentate ligand. That's why you're using di, right? Then En is there. That is ethane 1,2 diamine, but it's a didentate ligand. So we have to use bis or tris. Here it is bis because I have 2. Bis, you have to write a bracket. Ethane 1,2 diamine, right? Done. Then you go for the central metal atom, that is cobalt. Now we found that cobalt is going to be in plus 3 oxidation state. So plus 3, then you have the counter ion to be what? Chloride. This is how we named it. Guys, next question. Everyone be ready. I will ask one step to one people. Okay. We have Fe. Wait. So we can write Pt H2O twice Cl NO2. Okay. Right. So we ask. See, everybody has to answer one part of the thing. Right? Like whomever I ask. Okay. Just because I'm going to ask two people left. I don't know who the two people are. Okay. Akshaya, do you want to try now? Right? Can you ask me? Can you tell me which is the positive? Is it a positive charge ligand or a negative charge ligand here? Not ligand. I'm sorry. Is it a positive charge complex or a negative charge complex here? Akshaya. You can put the answer in the chat box if at all you find that your surrounding is too busy, too noisy. Yes, is it positive or negative? Or you can say, I don't know. That is also fine. Okay, and I don't know what's the problem. Anandita, can you answer the question? This particular thing, this one, is it a positively charged coordination complex or a negatively charged coordination complex?
Positive, sir.
Positive. Okay, fine. Fine. Anirudh, are you there? Can you answer the same question? Is it going to be a positively charged coordination complex or a negatively charged coordination complex? Anirudh, are you there? Okay, and I think Anirudh will chat. Anirudh says positive. Okay, fine. People, I think we have almost 8 students here, right? So does anybody wants to differ, saying that sir, no, this is negative charge to
neutrals.
Rohan, yes, you are right. This is neither positive nor negative. This is neutral, right, people? Right? Did I write any counter ion here? That means what? Here the overall charge of the complex is 0. We have seen this in classification. We can have the coordination compound to be a neutral coordination compound. Saying that, what do you mean by that? I can have 0 charge here. Okay, so the moment you see there are no counter ions, there are no counter ions on this side, neither this side, then that is understood that the coordination complex's charge is 0. Right? Okay, good, fine. Now let me ask whom I asked. I think Anandita I asked this time. Okay, Ananya, are you there, Kana?
Yes, sir.
Ananya, so what should be the first part of the name?
Diamine.
Amine. Where is amine? They are talking about this, right?
1 second, sir. I wrote the question.
Okay, okay. Now you not write the question. Now tell me, what is the name of this ligand first? Tell me, what is the name of this ligand? This ligand name H2O. What is the name of the ligand? Okay, fine. This ligand, I think this you should be able to answer. What is the name of this ligand? NO2. Okay, fine. And go to the next person. You will get your chance again, Ananya. Don't worry. Fine. Sashank. Right. Next one is Sashank only.
Sir, NO2 is nitrito.
Okay. Nitrito is right. Okay.
H2O aqua.
Good. Aqua. Right. So there are certain things you have to remember it like this, right? Okay. For H2O, it is aqua. For NO2, okay, someone is answering in the chat.
Sir, can you hear me?
Ananya,
My
yes,
computer actually went non-responding, sir, so I couldn't.
No issues. You're right. Aqua is absolutely right. Okay. Fine. And this I know is chloride. Oh, that's easy. Okay. Now let us go for the name. Maybe I will ask Mithun. Are you there, Mithun? Mithun, are you there? Okay, I think he's in the chat. Yeah. Can you just write the entire name now? Or you don't have to do the entire process. It will be so big. Just find the oxidation number of platinum here. Tell me the oxidation number of platinum in this complex. Three. Okay. Let us check. It is going to be 0. How is it 3?
So if NO2 is NO2 minus, right?
Yeah, NO2 minus, yes. Sir, mic is creating problem. No issues, Mithun, no issues. Right? So here you can write, right? X is this. For H2O, it is 0. For Cl, it is -1. For NO2 also -1. Overall charge is 0. Right? So X should be +2. I think he got this time, right? Yeah, 2 is correct. Right? Fine. So this is the overall thing. Right? Okay. Now we know everything. Yes, what happened again? I thought H2O as 1. That's a neutral ligand, right? H2O is a neutral ligand. So G0 is the charge. Good. Okay. Next, whom should I ask? Neha. Are you there, Kana? Neha. Okay, fine. I think Neha has some problem. Ashik, are you there? I think Ashik has already, I'm not able to see his microphone option. That means he doesn't have a microphone. Maybe he'll be able to answer in chat. Ashik, are you there? Okay, I'm not finding him. Fine, Rohan, you can complete the name. You can tell me the entire name now.
It's diaqua chlorido nitrito platinum twice.
Yeah, okay. Correct. Diaqua,
Chlorido nitrito platinum twice.
Yeah, platinum 3. Right? Okay. Now, people, remember this. There can be some some kind of problems coming whenever you have ambidentate ligand. I know NO2 is an ambidentate ligand. So whenever we write NO2, right, and whenever we write ONO, something like this also can come. The same thing. The overall formula is NO2 only, right? NO2, ONO, but nothing but you have to understand these are ambidentate ligand. Okay, so whenever they give NO2, you will write the name as nitrito N. This is how we write. The actual name should be nitrito N here because they have given NO2. Now, why are we writing this? It's because this is in this case, the nitrogen's lone pair is the one who is going to get donated. Okay, in this case, the nitrogen's lone pair is the one who is going to get donated. Okay, and in this case, whenever they give ONO, for this you have to write nitrito O. Because in this case, the oxygen is lone pair is the one which is going to get donated. Okay, and same way, we will write when I write Cn minus, right? When I write Cn minus, for this you will write cyanido C, because it is the carbon which is going to donate it. Or instead of writing it like this, you can write just cyanido for this, right? That will be better, no? Cyanido. And whenever you have Nc minus, Nc when we write, right? You can write isocyanido. Okay, cyanido, isocyanido. They'll mention the formula exactly like this: Cn, Nc in the formula which you write. Okay. Other than that, you can have NCS minus. Right now here, the sulfur is the one who's going to donate the this thing. What is that? Lone pair. Okay, so we'll write thiocyanito S. Right, and when we write NCS minus, now nitrogen is going to donate. We will write thiocyanate N. Okay, so these are all the small things which you have to remember. Okay, when they give NO2, ONO, how do you write? NCS, NCS, NCN, CN minus, NC minus. Again, and again nitrite, we are done, right? Yeah. So these are all the small things which we have to remember. Okay. Right. So that being said, maybe we'll just solve one more question and we'll wind up this particular thing. Okay, Iupac naming, right? And you can see there are so many questions in your book back. NCRT book back exercise has so many questions. You can solve all of them, right? And if you find any problem, you can always WhatsApp me. I'll be able to help you. Right. So next question is. See, I have seen this Iupac naming questions of coordination compounds directly coming in 5 mark in your board exams. Okay, so they'll give you 5 complexes. Okay, and they'll ask you to name all the 5 complexes. Direct 5 marks. I have seen questions coming. That's why we're spending so much time here. Okay, right? So don't think that we are doing it for no reason. Right. Okay. Say I have Ni, CO twice, Cl2, Br2. Okay, right. So now why are we doing only positive charges? Forget about it. I don't have a good book. All my books are there. I think I have a book. 1 second, please. Just give me 1 moment. One second, people. 1 second, I'll be back. I'm back. Right, let us take this complex. We have Cr, NH3. No, I saw something. Where is it? Ah, okay. Cr, NH3 5 times. NCS, right? And you have zinc, Cl4. Okay. Now remember, people, zinc has only one oxidation state. Zinc can exist only in +2 oxidation state. Okay. Zinc can exist only in +2 oxidation state. Okay. So that if you know, you can easily find what is the charge here, right? Right. If this is +2, right? If this is +2 and I have 2 -4, what should be the charge here? Basically here it should be +2, and if it should be -2, right? And here if it is -2, here it should be +2. Okay. So if at all you remember for zinc, you will be able to write the charges here. Okay. Zinc will always have only one oxidation state, +2. Okay. So here you have +2 and 4 chlorine. So 2 - 4 will become -2. Overall charge is -2. So here it should be +2. Okay. Fine. Go for it. Right. I'll give you 2 minutes time to answer this question. Okay. Good. So I'll ask, but we didn't have, what is the time? It's almost 8 o'clock. So people, I don't want to waste time. So anybody wants to give me the final answer?
Sir,
Yes, Kana.
sir, is it pentamine isothiocyanate chromium 3 tetrachlorozincate?
Tetrachlorozincate.
Zincate.
Okay. Last one thing is missing. Zincate. Avladana. Chromium, you have mentioned this thing, oxidation state. For zinc, why are you not mentioning?
Sir, 2.
That's it. Yeah, it's correct. Okay, perfect. Right. So Yeah, so you can
So
find the
previously
oxygen.
I couldn't answer because my laptop got hanged. So
No issues, Kana. No issues at all. No issues. Okay, good. Okay. So here, right? So we have chromium. We'll just find the oxidation state. So here we have X. Ammonia will have 0, right? Plus 0, and NCS is +1, right? So sorry, minus
Equal
1.
to +2, sir.
Yeah, -1, and overall charge is +2. So you'll write X to be +3. So cobalt is going to be in +3 oxidation state. So fine. So we'll write the we'll write the what is that, amine first, because that alphabetically that is what is going to come first, right? So we have penta amine, AMM, double M should come. Penta amine. You can write isothiocyanato, or you can write thiocyanato N. Like this also you can write. Okay, thiocyanato N, or you can write isothiocyanato. That is also correct. Okay, then we have what? Then we have chromium in +3 oxidation state, right? Then go for the other one, right? Now we have tetra chlorido zinc. Now we should not write with zinc. We have to end with 8 because it is negatively charged. Zinc 8, and obviously the positive, the overall oxidation number is +2. Right. Now, I just want to have one last question for Iupac naming, and then we are winding up. Okay. Right. So because this you should have seen, right? So if it's a simple complex only, but just that how do you write the name is very, very important. Right. So I have this complex, right? Can someone try and give me the name of this? You have Ag, Cn twice, minus, overall minus. Guys, your maths and physics portions are over in Epsilon.
No, sir.
No. Okay. Because once they complete, I think I'll take daily classes for you, I thought. So that will be able to complete the syllabus. So you have already completed electrochemistry. You have completed, what is that? Your carbonyl compounds, that is RDH ketones, carboxylic acid, and we are still here. And then we have what? We have chemical kinetics. Chemical kinetics is very small this time because say half portions are deleted, right? And then you have D and F block elements. D and F block elements, how we did for P block, like that we'll do, or we don't even have to do that because you will just get only one question from that. Okay, they will ask you only about this one, that lanthanoid contraction or actinoid contraction. Question one, if the question comes, right, you will only get questions only from this particular part, lanthanoid contraction and actinoid contraction. Nothing else you will get. Literally nothing else you will get.
Really, sir?
Really? Yes, really. Okay, right? So that is the question. Okay, but again, see, this has so much this thing, what is that, applications, right? Anna, like for even if you did not study this chapter at all, right, and whatever the question asked, and if you write the reason is lanthanol contraction or the reason is actinol contraction, 99% chance that you will get full mark for the question. 99%. Okay, right? Just because I told you now, do not go with so much lethargic, right? You at least go through the chapter once, right? See what they are telling and all, right? But compared to other chapters, this chapter, that is D and F block element, you don't have to give that much this thing, hard work for that. Okay, right? You, like if you go through the chapter once and you see if at all you have any doubts, ask me, because you will understand that some of the things given in the textbook are wrong. Okay, in NCERT textbook, say when you talk about the boiling point order will be correct only, but the reason they are giving for the order of boiling points or not is really not correct. Okay, so many will have returned to NCERT, but still they are not changing. I don't know why, right? So that's what for D and F block elements, mostly for any question asked, right? If you can write this one only, either, but you have to know which part goes for lanthanoid, which part goes for actinoid. That all you should remember, right? So that at least if you know, right, you will be able to write the answer as, okay, the reason is lateral contraction or action contraction only. Okay.
So for the question, is the answer dicyanide or argentate twice?
Yes, that's correct. Yes. This is absolutely right. So we have to write the ligand first, that is dicyanide or dicyano, however you want to write. Okay, and then Ag, if you write silverate, right, that is absolutely wrong, right? It's like iron, right? You cannot write ionate. What you wrote? You wrote ferrate, right? So like that, here you have to write what? You have to write argentate. And if you find the oxidation number, it is going to be +1. +1. Right? It's easy, right? So we have x minus 2 is equal to -1. X is going to be +1. Okay. Now instead of Ag, if I have given Au gold, then what it will return? In this place, what should come? Instead of argentate, if instead of Ag, that is silver, if I gave you gold, what should come here? What should be the name? Okay, you should write it as orate. Okay, you should write it as orate. Okay, that's the name you should use when the coordination complex is negative and the central metal atom is going to be what? The central metal atom is going to be gold, orate. Right? Say when I write lead, if lead was the, you will not get 99%, but still if you get, then what will you write here? Right? You should write it as plumbate. Okay, you write it as plumbate. Again, Fe we already know. Fe is going to be ferrate. Right? Other than that, anything else is there? Yeah, tungsten. You will not get again. Mostly, you will write it as wolframate. Okay, don't worry about this. Okay, this is all are maybe for your JEE mains or JEE advanced or NEET exams, right? But again, plumbate also you don't have to worry. But these three things, Ag, Au, and Fe are very, very important. Okay, fine. So that is about the Iupac naming. Done. Okay, right. So now what we'll do is we'll move on to the isomerism part. Okay, right. So isomerism, just like how you did in the case of organic chemistry, right? Isomerism can be of two types, right? So we can have something called as structural isomerism, right? And then you can have stereo isomerism. Right? So stereoisomerism obviously is going to be same molecular formula, but different 3D structures. Right? Or I can say different orientations. Right? How do we define isomerism? Isomerism is in general defined as it is the phenomenon where the compounds have same molecular formula, but different structural formula or different orientations of atoms in 3D space. Right? You want the definition, you can take down. Maybe I'll repeat one more time. Take down the definition, people, for isomerism. It is the phenomenon of compounds. It is the phenomenon of compounds having same molecular formula. I think the charge is less. Just a moment. Right? Same molecular formula, but different structural formula. Or
Excuse me, sir.
yes, Kanna.
So I think isomerism is deleted this year.
Oh, isomerism is deleted. Oh,
I
great,
think
great.
so, sir.
Okay, can
Yes,
somebody
it's
confirm?
deleted. It's deleted.
Okay. What other things deleted here in coordination complex? Only this
The last part, so like the
Metal carbonates.
application.
application. Okay, metal carbonates, organometallic compounds is there.
I have to check, sir.
1 second, sir.
Yeah. Check. Thank God you told me, or else you would have spent at least 2 classes on this. 3 hours would have gone on isomerism.
Metal carbonyls is there, sir.
There.
Only the applications is, and the
Oh,
isomerism. is there.
Isomerism and application related. Okay, good, good. Fine. Then we will directly go for bonding. Okay, so now we have studied how to name the Iupac, how to name the compounds with Iupac nomenclature, everything, right? And obviously stereoism, isomerism, if it was there, we would have isomerism also. Then we would have gone for this bonding. How exactly is the bonding? What is the bonding happening? Like say what type, we know what type of bond is happening. We know that inside the coordination complex, it is always going to be a coordinate bond, right? But how exactly? And how exactly is the structure? What is the shape? What is the geometry? What is the strength of the bond? Right? You have something. We have something called as strong ligands. You have something called as weak ligands. Right? So all those. If at all we have a strong ligand, what is going to happen? If at all we have a weak ligand, what is going to happen? All those things we'll study here. Right? In bonding, when I say bonding, we are going to study about all the bond characteristics in a coordination compound. Okay, so like how you had in chemical bonding, right? When in the 11th class, how you had in chemical bonding, we have different theories, right? So here also we are going to have different theories coming into the picture. Okay, so first one, right? In this is your valence bond theory. Okay, first one is your valence bond theory. So basically, they did not mention this, but this is an updated version of valence bond theory. Okay, basically why I say updated is this is including VACPR3. Okay, this is including VACPR plus your theory of hybridization. Right, everything together. Okay, everything together, we have this particular theory, valence VB theory, we call it valence bond theory. Right, so I don't know how much you remember. Right, theory of hybridization, valence bond theory, VACPR were actually different theories initially when they came. Right, different scientists actually proposed this. Right, even when I taught you in 11th, this is the way I taught you. I said that valence bond theory is something else. Right, theory of hybridization is something else. VACPR is something else. But again, people nowadays use it, alternatively for different names. Right. But anyways, so when I say valence bond theory, all the things are included. VACPR, theory of hybridization, and the overall valence bond theory, everything is included here. Okay, right. So we know how hybridization works, right? We already know how hybridization works, that we know, right? So here we are not going to have so much difficulty because we are going to see only two things in coordination complexes. Even in the case of your valence bond theory, as well as the next one, that is the crystal field theory. We have two theories only in this bonding, right? One is valence bond theory. The other one is going to be crystal field theory. But other than that, you have still more superior theories. You have something called as ligand field theory, right? And you have something called as molecular orbital theory. Yeah, molecular orbital theory exists for coordination complexes also. Okay, but again, those things are not there in your syllabus, right? That is little for higher levels. Maybe if you take chemistry as your major in your bachelor's, then maybe you'll study all that. Okay, so as I said, we are going to do only for two coordination numbers, coordination number 4 and coordination number 6, right? Only these two we will be concentrating, not only on valence bond theory. Even when you go for crystal field theory, only these two we will concentrate. Other things we don't have to worry about, right? Okay, so coordination number 4 can have two different. Just 1 minute. Okay, so coordination number 4 can be of two types. Okay, one, it can have a geometry or shape to be square planar. Is it right? Yeah, square planar, or it can be tetrahedral. Okay, now we know what is the difference between these two shapes, right? Say if at all I have like AB4, a ligand like this. Okay, right, that is A is the central metal atom, B is the ligand. Okay, right. So depending on the conditions, it can have two different shapes. One looks like this: A, B, B, B. Now it is all going to be in the same plane. Basically, if at all you're using your phone or your laptop screen, the center of your laptop screen, we are going to have A, and the four corners, right? Or say, let me show you here. Right, in this book, if you take, right, in the center, we are going to have this A, four corners, right? We are going to have B, square in the same plane. That is one possibility, right? Okay. The other possibility is we can have tetrahedral shape. We know how tetrahedral looks, right? So we need to have something like this. Two bonds will be in the same plane, right? And two other bonds, right? Two other bonds will be protruding towards you and going away from you from the plane. Right? This is the shape of tetrahedral. This is square planar. Right? This is tetrahedral. All right. Okay. So now if you remember what now this, okay, this wedge represents what? This represents what? This wedge, when we wrote, what does it represent? Anybody knows? Really? Okay. So this wedge, whenever we write a wedge like this represents that the bond is coming towards you. Coming towards
the paper. It's out of the paper.
Yeah, out of the paper. That is out of the paper towards you. Right? Say if I talk with respect to the laptop screen, it is coming towards me like this. Right? Okay. Whenever we write a dashed line like this, that the bond is going away from you. Going away from you. Okay. That means it is going, the laptop screen is here. Okay. It is going behind the laptop screen. Right. So if I have to properly explain, you say this is your, say this is A, the tip represents A, one bond here, another bond in the same plane, this bond. Okay. In the same plane. Assume that this is, let me put, how do you put it here? Okay. I don't want to confuse you. Anyways, so you have the tip A, right? And then you have one B at the top, one B at the bottom in the same plane, right? The plane of the paper which you're seeing, right? One bond is going to come like this. Okay, one bond is going to come like this. The other bond is going to be behind it. Okay, it's like a tripod stand. If at all you want to properly imagine this, you can imagine a tripod stand. I don't know during this pandemic whether you have gone to the lab or not, right? You might have seen a tripod stand. Tripod stand, one bond will be coming here, two other bonds will be going like this, one will be at the top, right? So that is what is a tetrahedral structure. Okay, right. So now, right? So as I told, for coordination number 4, you can have two things, that is square planar or tetrahedral. For octahedral, for coordination number 6, there is only one shape possible, and that is octahedral. Right? For that, only one shape is possible, that is octahedral. Octahedral can also be called as, any guesses? Octahedral can also be called as? Can also be called as? Okay, it can also be called as square bipyramidal. Right, square bipyramidal. Right, so how the shape looks, right? Say, look at this. Say in the center, right? In the center of this, I'm going to have A. Okay, in the center, I'm going to have A. In the corners, 1, 2, 3, 4 corners, we are going to have B. Right, one B is going to be at the top, right? And another B is going to be at the bottom. Right, that's why we say one square, right? One pyramid at the top, another pyramid at the bottom. That is why we call it as square pyramidal, right? So if I have to mention this in 2D, this is how it is going to look. So we have A, like this is going to be one plane of your screen, right? All the B's are going to be in the 4 corners, right? And one B is going to be at the top, the other B is going to be at the bottom. This is your shape for octahedral, or it is also called as square bipyramidal, right? Okay, right? So these are the only things you're going to see. The only 3 possibilities, either square planar or tetrahedral or octahedral. That's it. Okay, right. Now people, what you have to understand is whenever you want to have square planar complexes, right? Whenever you want to have square planar complexes, the hybridization can be of only one type, right? Or whenever you have coordination number 4, there are 2 possibilities of hybridization for the central metal atom. Again, please understand, whenever we talk about hybridization, we do talk about hybridization only for the central metal atom. right? Not for the ligands, not for anything else. We say that nickel is this hybridized. We say iron is this hybridized. We say chromium is this hybridization. We cannot say, amine is this hybridized. That doesn't make sense at all, right? In the coordination complex, for which we talk about hybridization, only for the central metal atom we talk about hybridization. Even in the case of chemical bonding, I've told you, only for the central atom, whatever is central atom, that for that only we can choose the hybridization. Okay, fine. So whenever you have square planar complexes, the hybridization should be DsP2. Okay, whenever you have DsP2 hybridization, the complex will be a square planar complex, right? And what you have to understand is this D comes from n-1th orbital, n-1th orbital, right? And this S and P comes from the valence orbital or valence shell, right? Or instead of orbital, you can write n-1th shell, that is penultimate shell, and this S and P comes from the valence shell. Okay, right? Now, and also, since we are using n-1th, so that is inner shell, these kind of square planar complexes can also be called as inner orbital complexes, right? Since we are using not the valence shell, but the d orbital is going to come from this thing. Since the d orbital is going to come from the inner shell, it can also be called as inner orbital complexes. Okay, right? And in the case of tetrahedral, we know what is the hybridization. You have already seen in your chemical bonding as sp3, right? And both this S and P will come from the valence shell, no doubt about it. Okay, it is going to come from valence shell. So since we are using only valence shell, they can be called as what? They can be called as outer orbital complexes. Outer orbital complexes. Okay, right. So that is about your square planar complexes and tetrahedral complexes. You need to have DsP2 for your square planar. For tetrahedral, we need to have sp3. And this D, which is there in your DsP2, that is square planar, that D comes from the inner shell. That is why you're going to be calling it as inner orbital complexes, right? Okay. Now, when we go for octahedral complex, I don't have space, so let me write it here, right? So whenever we talk about octahedral complexes, here also we have two possibilities, but both the possibilities will give you octahedral only. Okay, here also there can be two different hybridizations possible, right? But even though we have two hybridizations possible, we can have both of them to have octahedral shape or geometry only, right? So first one is sp3d2, right? Or we can have d2sp3. Now, what is the difference here? All the three orbitals, that is sp and d, come from the valence shell, so they can be called as outer orbital complexes. Outer orbital complexes, right? And you understand that this D alone is going to come from the inner shell, or say the n-1th shell, right? And this S and P comes from valence shell, right? So since you're using the inner d orbital, they can be called as inner orbital complexes. Okay, they can be called as inner orbital complexes. Okay, right? Now, how exactly are we going to do hybridization? Maybe I'll just give you a teaser trailer, right? Not with respect to a coordination complex, right? But it is going to be with respect to something else. We'll take a normal compound, right? Now, what we understand is inside the coordination sphere, all the bonds are going to be coordinate bonds, right? All the bonds are going to be coordinate bonds, is it not? Right? So now what we do is we will take the example for BF4 minus and try to understand how, in a hybridized orbital, in case of hybridization, how can we talk about, I mean, how to put it? In case of a hybrid orbital, how a coordinate bond looks like, right? That is what we're trying to understand here. We already know what is a coordinate bond. Instead of two electrons mutually getting shared, both the electrons are going to come from one atom, right? Okay, right. Let's try to understand here. Now, how do you find the hybridization here? Now, hybridization, I think you know one formula for finding hybridization, but that is not going to be useful. But anyways, I'll tell you now. There's something called as steric number. Steric number is equal to number of atoms bonded to the central atom, Ca central atom, plus number of lone pairs in the central atom. Okay, you have to add two things here, right? Number of atoms bound to the central atom plus number of lone pairs in the central atom. Okay, now in this case, and depending on the steric number, say if you find the steric number to be 2, it is sp, 3 means sp2, 4 means sp3, or again in this case we can also have dsp2, 5 means we can have sp3d, like that we'll be able to do, right? 6 means sp3d2, so on and so forth, right? Now we don't have dsp2 in your normal compound, only in coordination complex we have dsp2. Now fine, like now let me find the steric number here. Now central atom is boron, right? Now the first part of the formula talks about the number of atoms bonded to the central atom, right? Number of atoms bonded to the central atom. To bromine, how many atoms are attached? 4 fluorine atoms are attached. Is it not? 4 fluorine atoms are attached. Plus number of lone pairs on the central atom. Like, please understand, fluorine can have lone pair, but we are not talking about that. We're talking about whether boron can have lone pair. The answer is no, it doesn't have any lone pair. The steric number is 4. So 4 means this boron is going to be sp3 hybridized. Okay, this boron is going to be sp3 hybridized. Okay, now let us write the structure, let us write the electronic configuration of boron, right? So boron is basically going to have boron atomic number 5, right? So it is going to be 1s2, 2s2, 2p1, right? 1s2, 2s2, 2p1, right? So we are worrying about only about the valence shell, right? Do not worry about this 1s2, right? Only the valence shell you have to take into account, right? So we can have 2 electrons in 2s, and we have 1 electron in 2p. No issues, right? Then what do we do? Well, whatever the electrons are paired, we unpair them. We shift it to the next higher energy orbital. We'll shift it here, right? This is your ground state, GS. When I go to the excited state, what is going to happen? In 2s, okay, in 2s, we are going to have only 1 electron, right? And in 2p, now we had 2 electrons. This is your 2p. Okay, right. Now, we already understood the hybridization. Hybridization for boron is going to be sp3, right? That means 1 s orbital and 3p means not the 3p orbital, 3 numbers of p orbitals. That is, I can write like this, s plus p1 plus p2 plus p3, that only will form sp3 hybrid orbital. Is it not? Right? We need to have 3 numbers of p orbitals combining with s orbital to form sp3. No issues, right? Okay. Now what we have? We have 1 s orbital here, 1, 2, 3 p orbitals here, right? Now all of them will combine together to form hybrid orbitals, right? Now another important thing about hybridization is the number of atomic orbitals combining should be equal to the number of hybrid orbitals formed. That means in this case, totally how many orbitals are you combining? You're combining 4 atomic orbitals, that is 1 s and 3 numbers of p, right? So you need to have 4 numbers of sp3 hybrid orbital also to be formed. That's why we say this, right? Number of atomic orbitals formed should be equal to the number of atomic orbitals combining should be equal to the number of hybrid orbitals formed, right? So in this case, we are combining 4 atomic orbitals. So we need to have 4 hybrid orbitals also. No issues, right? So when these two combine, obviously we are going to combine all of them here, right? So what is going to happen, right? We are going to have 4 numbers of sp3, 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 and sp3. Okay, these are your hybrid orbitals. 4 numbers of sp3 hybrid orbitals are formed, right? Now, each of them. Now, you understand that 3 of them, that is 1, 2, and 3, right? 3 of them are actually having 1, 1, 1 electron, right? And the other one is completely empty because you understand here there is nothing. It's completely empty. Okay, right? If that's the case, right? Now, what can I understand is there are 4 fluorine atoms. Right, the formula is BF4 minus, right? BF4 minus means there is going to be 3 fluorine atoms, and one of the fluorine atom is going to be in the form of F minus, right? One of the fluorine atom is going to be in the form of F minus. Okay, right. So now this fluorine atom is going to donate 1 electron, another fluorine atom is going to donate 1 electron, another fluorine atom is going to donate 1 electron. So 3 normal covalent bonds are okay, right? 1 electron coming from boron, another electron coming from fluorine. 3 such bonds are there, right? But this F minus, you know what it is going to do? It is actually going to donate 2 electrons, both coming from fluorine, and this is a coordinate bond. Okay, this is a coordinate bond, right? Now you don't have to believe me. Okay, we will go for your Lewis dot structure and decide this. How exactly is Lewis dot structure? Okay, so we have boron. Okay, we have boron. Boron is having what? 2, 3 configuration, right? 5 total atomic number, 2, 3 configuration. So it has 3 electrons in its valence shell, right? Now we have fluorine atoms, right? Fluorine is having 2, 7 as the configuration. This is for boron having 2, 3, right? So it has 7 valence electrons, right? 1, 2, 3, 4, 5, 6, 7. Same way, another thing. 1, 2, 3, 4, 5, 6, 7. Same way, 1, 2, 3, 4, 5, 6, 7. No issues, right? Now I told you BF4 minus means 3 of them are fluorine atoms and 1 of them is going to be F minus, right? So if I write F minus, right, now that needs to have 8 electrons. Is it not? Because 1 electron is getting added, so it should be 2, 8 configuration, right? So we can have 1, 2, 3, 4, 5, 6, 7, 8. No issues. Okay. Now this fluorine atom requires 1 more electron to satisfy its octet, so it will take up this electron. Now this fluorine atom requires 1 more electron to satisfy its octet. It will take up this electron. This fluorine atom requires 1 more electron to satisfy its octet. No issues, right? Okay. Now, how many ever electrons the boron accepted, that many electrons it can take. That means it has given 1, 1, 1, 3 electrons. So it can take up this, and this electron. Totally, if you check how many electrons boron will have, already it had 3 electrons, 1, 2, 3 in the valence shell. Now 3 more electrons are going to come from fluorine, totally making 6. Is it not? But still, octet is not satisfied, right? But still, octet is not satisfied. So what is going to happen now, people? We are going to take up these electrons, no doubt. Boron is going to take up these 3 electrons, no doubt at all, right? But still, it is having only 6 electrons. So what is going to happen is that this is already octet satisfied. This F minus already has 8 electrons. These 2 electrons are going to be donated to boron, so that it is going to have 8 valence electrons. That is already satisfied. For this already 8 electrons are there, so no issues, right? So these 2 electrons which are there here will be donated to boron in form of a coordinate bond, and such that the boron is also going to get octet satisfied. So how do we represent the bond formation now? We have 3 fluorine atoms normal, right? And 1 of the fluorine atoms alone is going to be in the form of F minus, and that is going to form a coordinate bond. You understand? Okay, so we have established the fact that in the case of BF4 minus, there is 1 coordinate bond. There is 1 coordinate bond. Now, if you look at the hybridization, right, that is that there is actually a connection between the number of coordinate bond and number of hybrid orbital. Not just the hybrid orbital, but the number of empty hybrid orbital. Now you look at this, right? So in one of the hybrid orbital, what happened? It was empty, right? All the others had 1, 1, 1 electron. Okay. Now this normal 1, 1, 1 electron, what they have, they are going to form normal covalent bonds, right? Now this empty hybrid orbital is the one which is going to take part in the coordinate bond. Okay. Now I can tell this. The number of coordinate bonds in a molecule is equal to number of empty hybrid orbitals. That's the whole point. Number of empty hybrid orbitals. Okay. How many ever hybrid orbital you have, that many coordinate bonds that particular metal, central metal can have. Right. In this case, boron had 1 sp3 hybrid orbital to be empty. So it was able to form 1 coordinate bond, both the electrons coming from fluorine, like this, right? So in case of coordination complexes, what you are going to see, the hybrid orbitals which you are going to form all of the hybrid orbital is indeed going to be empty. Why? Because all the bonds are formed only coordinate bonds. Is it not? So if at all you have coordination number 4, that means you need to have 4 empty hybrid orbitals. 4 empty orbitals should be there. If at all you have a coordination number to be 6, means what? You're going to have 6 coordinate bonds. That means you need to have 6 hybrid orbitals to be empty. Okay. So next class we'll be taking up from here. Right? We understood that how do you form the hybridization? What are the criteria for forming a coordinate bond? The only criteria is that the hybrid orbital should be empty. As simple as that. Right? So this is what we will take. Now we saw in the case of a normal compound, we will take coordination complexes and try to understand it in a little more better way. Okay. Anybody has any questions? Okay. I hope everybody is following. We'll stop with this for today. Okay. Right. Fine people. Thank you so much. We'll meet on Sunday.
Thank you, sir.
Thank you so much.